Welcome to the second lecture on limits. So, in the first lecture we gave the meaning of limits, and then we also saw the rigorous epsilon delta definition of limits, and then we were looking at some of the properties. So, today I will continue with some more properties of limits, and then we will state some more results. So, we will continue with properties of limits continued. So, last time we saw the sum difference rule and then the multiple of a constant. So, today let us see what happens to the limit of the product of function. So, product rule. So, this simply says that if limit of x going to a f of x and limit of x going to a g of x exists, then limit of the product function f x times g x, this also exists, and the limit of the product is equal to the product of the limits, this times limit of g of x as x goes to a. So, that is limit of the product is the product of the limit. Again, this can be proved using the epsilon delta definition, but we will skip the proof. Rather, let us see that using this, let me state this result. So, suppose p of x is a polynomial with real coefficients, that is p of x is of the form a constant a 0 plus a 1 x plus a 2 x square, so on up to a n x to the power n. Then the limit of p of x as x approaches any a, this is equal to p of a. So, to prove this you only have to know. So, first note that limit of x going to a of x, this is equal to a, right. This is very easy to see, and using epsilon delta definition you just have to see that delta equal to epsilon will work. So, the limit of the function f x equal to x, the limit at x goes to a is equal to a. So, using this, so therefore, the limit of x square as x goes to a, this will be equal to simply a square by the product rule. and by induction limit of x to the k x going to a, this is equal to a to the k for all k in natural number. So, therefore, the limit of p of x as x goes to a is equal to, first of all this I can write as limit of a 0 plus limit of a 1 times x and so on up to limit of a n times x to the n as x goes to a. This is by the sum rule. And then you use that limit of a constant time a function is constant time the limit. So, this implies limit of p of x as x goes to a is equal to limit of the constant is simply a 0 plus a 1 times the limit of x as x goes to a plus a 2 times limit of x square x going to a, so on up to a n times limit x to the n as x goes to a. This is equal to a 0 plus a 1, the limit of this is simply a plus a 2 times a square and the limit of x to the n is a to the n, but this is nothing but the value of the polynomial evaluated at a p of a. So, hence we are done. So, for example, if we want limit as x going to say 1 of x square plus 3 x plus 2, then you can just write this as the value of the polynomial at 1. So, that is 1 square plus 3 times 1 plus 2, which is 1 plus 3 plus 2, which is 6. Right. Next rule is about the quotient of two functions. So, suppose limit of x going to a f x exists and limit x going to a g of x, this also exists. Further, and is not equal to 0. Then the limit of the quotient of these two functions f x by g of x, this is equal to limit of f of x by limit of g of x. Right. So, this is the result, but if the limit of the denominator g of x, if that is equal to 0, then division by 0 is not defined. So, of course, we cannot write this, but if the limit is non-zero, then this makes sense and we can use this formula that limit of quotient is the quotient of the limit, provided the limit of the denominator is not equal to 0. So, this means that is the limit of the quotient of two functions equals the quotient of the limit if the limit of the denominator is non-zero. So, for example, if we have to calculate limit of say x cube plus 2x plus 3 divided by x square plus 1 as x approaches 1. So, here first you see that what is the limit of the denominator as x approaches 1, x square plus 1 is polynomial. So, the limit of x square plus 1 is 1 square plus 1, which is non-zero. So, this I can write that since limit of x going to 1 x square plus 1, this is equal to 1 square plus 1, which is 2, this is non-zero. Therefore, the limit of x going to 1 x cube plus 2 x plus 3 by x square plus 1 is simply the quotient of the limits and now both are polynomials. So, we know that we just need to evaluate it. So, at x equal to 1 we get 1 cube plus 2 plus 3, this is 6 divided by 2. So, this is 3. Let me warn you, we said that if the limit of the denominator function is non-zero, then the limit of the a quotient exists and equals to the quotient of the limit. But if the denominator function limit is 0, we cannot say that the limit does not exist. So, the limit of f x by g x, this might exist even when limit of g of x is equal to 0. In fact, we will see that most of the important examples will be when the limit of the denominator is actually equal to 0. So, for example, find limit of x going to 1 x square minus 3 x plus 2 divided by x minus 1 if it exists. So, here we see that the limit of x going to 1 of x minus 1, this is simply 1 minus 1, which is 0. Also, so we cannot use the directly the quotient rule. So, we cannot use the quotient rule directly, but if we see the numerator, limit of numerator that is again 1 square minus 3 times 1 plus 2, which is also 0. So, the limit of the numerator and denominator both are 0. In fact, here we see that at x equal to 1 the numerator and denominator both are 0. So, therefore, x minus 1 is a factor of. So, here x square minus 3x plus 2 divided by x minus 1, this is equal to x minus 1 times x minus 2 divided by x minus 1. Of course, this is defined if x is not equal to 1, and if x is not equal to 1, then one can cancel this x minus 1, and this is equal to x minus 2 if x is not equal to 1. So, the limit of x tends to 1 of x square minus 3x plus 2 by x minus 1, this is same thing as limit of x approaching 1 of x minus 2. Because remember that while calculating the limit, we do not have to consider the value of the function at x equal to a, we only need to know when x is sufficiently close to 1. So, this is equal to, again this is just a polynomial. So, this is 1 minus 2, which is minus 1, right. So, in this example we see that even though the limit of the denominator does not exist, the limit of the quotient might exist, right. So, this is one way of trying to find the limit. Let us do one more example. So, what is limit as x approaches 4 of x minus 4 divided by square root x minus 2. So, here the function is, so here we have this function f of x equal to x minus 4 divided by square root x minus 2. This is defined for any x which is greater than equal to 0, but x not equal to 4, right. So, if I take an interval, and any interval which any interval around 4 which does not contain negative integers, negative real numbers, then this function is defined and we want to know what is the limit. So, we can talk about the limit of this function. So, note that this is again we can simplify. So, we can multiply and divide by square root x plus 2, this is the conjugate of square root x minus 2, to get f x is equal to x minus 4 times square root x plus 2 by square root x minus 2 times square root x plus 2. And now, if you multiply in the denominator, we get x minus 4, and this cancels with this. So, f x is equal to square root x plus 2 if x is greater than equal to 0 and x not equal to 4. So, therefore, limit of f of x as x approaches 4 is equal to limit of this function square root x plus 2, which is same as the function f of x in a small enough interval containing 4 excluding x equal to 4. So, this is equal to square root 4 plus 2, which is 2 plus 2, which is 4. So, this is another way of calculating limits when you get the limit of the numerator and denominators are both 0. So, next what we will do is this theorem. This is called the sandwich theorem, or sometime it is called the squeeze theorem. So, what this says is that suppose we have a function f of x, suppose f of x is greater than or equal to g of x and is less than or equal to h of x for all x in an interval containing a but maybe excluding x equal to a. So, suppose f x lies between these two functions g of x and h of x in an interval containing a. Also assume that the limit of g of x equals the limit of h of x, and both are equal to say L. So, if the limit of the function g of x and h of x are both equal to L, then the conclusion is that then limit of f of x as x approaches a, this exists and it equals again the same limit L, right. So, if you see using a graph, so what this says is that suppose you have a function such that in some interval this f x is between two functions g of x and h of x, and the limit is same, right. So, in this case let me draw this in. So, we have f of x and we have g of x and h of x. So, in case that the limit at this of the upper function h of x and the lower function g of x, if they are both same, then the limit of f of x is also same. So, remark the sandwich theorem can be proved using the epsilon delta definition. So, I would suggest that the students can try to prove this using this definition, but we will skip the proof, rather we will let us say that this is very important. So, this theorem is extremely useful in computing limits. So, many times what happens is that the function whose limit you want to calculate, it might be complicated, but if you can find a smaller function and a bigger function and you can easily calculate the limits, and if the limits are same, then this also has the same limit. So, we will see an important limit using this theorem. So, as an application, we will prove that limit of the function sin x over x as x approaches 0, this is equal to 1. So, this is a very important formula for limit, that limit of sin x by x at 0 is equal to 1. Note that here we cannot use, note that we cannot use the quotient rule, because limit of the denominator is 0, limit of the numerator is also 0, and here we do not have polynomials that we cancel x and then try to use the quotient rule. So, rather what we will do is that we will prove that this limit is equal to 1 by using sandwich theorem. So, to do that, let me first draw a circle of radius 1. So, I have a circle and the radius of this circle is 1. So, I have this is 1, this is 1, and now let us take an angle equal to x radian. So, this is x in radian, and let me draw this triangle, this, and let me join these 2 points, and we will also extend this and then draw a perpendicular here. So, let me mark these points. So, I have O here, A, this point is B, this is C, and this is D. Consider a circle of radius 1 and let x be an angle in radian and consider the figure drawn to the left. Now, let us try to, so from this figure it is clear that if I look at the area, so area of triangle OAB, this is less than area of sector OAB, which is in turn less than area of the bigger triangle OAD. right. So, we have this is the sector, this is a fraction of the whole circle, and of course, the triangle OAB, this area is less than the area of this sector, and this sector is again contained strictly between this triangle OAD. So, we get this, right. Now, let us see what are these areas. So, we have this. Now, area of triangle OAB is equal to half times the base is OA times BC, right, which is equal to half the length of OA is 1, this is 1. What is the length BC? So, note that this angle is x. So, this length BC is nothing by sin x, right. Sin of x is nothing but the ratio of the opposite side and the hypotenuse, which is 1 here. So, sin of x is BC divided by 1. So, BC is equal to sin x. So, this is half times 1 times sin x. So, we get area of triangle OAB is equal to half sin x. Now, what is the area of the sector? Area of sector OAB. So, the area of the sector is in the ratio of the area of is in the ratio of the angle. So, we have the angle is x divided by the total angle of the circle is 2 pi radian. So, x divided by 2 pi into area of the circle. Right. For 2 pi angle we get the whole area of the circle. So, for x angle we get x divided by 2 pi into area of the circle. So, this is equal to x divided by 2 pi, area of the circle is nothing but pi times the radius 1 squared. So, this gives me just half x. So, area of sector is half x, and we also need area of triangle OAD. So, this is again a right angle triangle, and the area is half times OA times AD. Let me show the picture again. So, the triangle OAD, the area is half times OA times AD. What is the length of AD? In this triangle OAD, if we see, this base is of length 1. So, this opposite side is of length tan x. So, this is equal to half times OA times AD. So, that is half times 1 times tan x. So, this is half tan x. So, what we get is that, so for any x between 0 to pi by 2, we have that area of triangle OAB is half sin x is less than area of the sector, which is half x, which is less than half times tan x. Right. This is true for every angle x which is between 0 and pi by 2. Now, what we do is that we divide throughout by by sin x. If x is between 0 and pi by 2, sin x is positive. So, dividing by this, what we get is so first let me cancel this half from each of this. So, we get sin x is less than x is less than tan x, and then dividing by sin x, I get 1 is less than x by sin x, which is less than tan x divided by sin x. But tan x is sin x divided by cos x. So, this is equal to 1 by cos x. So, the conclusion is what we get is, so 1 is less than x by sin x, which is less than 1 by cosine of x for every x between 0 and pi by 2. Now, if we take the reciprocal, this implies that if I take the reciprocal, the inequality changes. So, we get 1 is greater than sin x by x, which is greater than cos x for all 0 less than x less than pi by 2. Right. So, this is a very important inequality. So, we have got that. Let me write this again, cos x is less than sin x by x, which is less than 1, if 0 is less than x is less than pi by 2. Right. What we were looking for is the limit of sin x by x. What we did is, we have found that sin x by x is between cos x and 1 for all x between 0 and pi by 2. So, also if I replace x by minus x, we note that cos of minus x is nothing but cos of x, and sin of minus x divided by minus x, because sin is an odd function, this is minus sin x divided by minus x, which is again equal to sin x by x. That is both cos x and sin x by x are even functions. So, if x is negative, then minus x is positive. So, because we have this inequality 1, so hence from 1 the inequality is in fact true for any x between minus pi by 2 to pi by 2. Right. So, now we got an interval containing 0 in which we have this inequality that sin x by x is greater than cos x and less than 1. Now, we just need to know what is the limit of cos x and limit of 1 as x approaches 0. Since limit of cos of x as x approaches 0, this is equal to simply cos of 0, which is 1, and of course, the limit of the constant function 1 is equal to 1 by the sandwich theorem. the limit sin x by x as x approaches 0, this is also equal to 1. So, we have proved that this limit is equal to 1 by bounding this function between two functions cos x and 1, whose limits are easy to calculate, and then we know that this limit is also equal to 1. So, this is a very important formula for limit, and you can use this to calculate many limits. So, we will do some examples using this formula. So, one is, if I write limit of tan x by x, this is equal to what? So, note that tan x by x, this is equal to sin x by x times 1 by cos x, right, if x is not equal to 0, and we know that limit of sin x by x, this is equal to 1, and limit of 1 by cos x, this is equal to 1 by limit of cos x is 1. So, this is also 1. So, by the product rule, limit of tan x by x, this is also equal to 1. Another one important limit is, what is this limit of 1 minus cos x divided by x? So, here we have that as x goes to 0, the limit of the denominator is 0, the limit of the numerator is again 1 minus 1, which is 0, and we want to calculate this limit. So, recall from trigonometry, we can express cos of an angle in terms of sine of half of the angle, right. So, cos of 2a is equal to 1 minus 2 sine square a, right. Cos of 2a is cos square a minus sine square a, which is equal to 1 minus 2 sine square a. So, that is 1 minus cos 2a is equal to 2 sine square a. So, therefore, 1 minus cos x is nothing but 2 times sine square of x by 2. So, the numerator is equal to 2 times sine square x by 2, denominator is x. So, 1 minus cos x by x, this is equal to 2 sine square x by 2 divided by x if x is not equal to 0, and then we can write this, this is equal to sine of x by 2 divided by x by 2 times another sine of x by 2, right. I just brought this 2 in the denominator. So, I get x by 2 here. So, therefore, limit of x going to 0 of 1 minus cos x by x, this is equal to limit of x going to 0 of sine x by 2 divided by x by 2 times the limit of sine of x by 2 as x goes to 0. provided these two limits exist, right. So, now what we know is that limit of sin x by x as x approaches 0, that is equal to 1. Here what we have is sin of x by 2 divided by x by 2. So, if we put y is equal to x by 2, then as x tends to 0, y also tends to 0, because y is half of x. So, therefore, this limit x going to 0 of sin x by 2 divided by x by 2 is equal to limit of sin y by y, where y is approaching 0, and this limit we know is 1, and of course, the other limit of x going to 0 of sin x by 2, this is equal to sin of 0, which is 1, which is 0. So, therefore, limit of 1 minus cos x by x, x going to 0, this is equal to 0. So, we saw three limits in terms of trigonometric functions. So, one is sin x by x, limit as 0 is 1, and using that limit of tan x by x at 0 is also 1, and limit of 1 minus cos x by x, that is equal to 0. So, some other example using these formulas. So, what is limit of tan of 2x divided by sin 3x. So, what we can do is that this is equal to, we can write tan 2x divided by 2x and then multiply it by 2x. If x is not 0, then I can write tan 2x as tan 2x by 2x times 2x. Similarly, sin 3x can be written as sin 3x by 3x times 3x, and then we have limit as x goes to 0. Now, in this one 2x by 3x, if x is non-zero, I can cancel these x, and then we know the limit of tan y by y as y approaches 0, that is 1, limit of any sin y by y as y approaches 0, that is also 1. So, this is equal to, the constant can be taken out from the limit. So, 2/3 limit of x going to 0 tan 2x divided by 2x and then divided by limit sin 3x divided by 3x, which is equal to 2/3. We have seen that both the limits are 1. So, this is equal to 2/3. Another example, find limit of x going to 0 of sin 3x divided by x. So, many students make mistakes thinking that this sin of 3x, this is going to 0, x is also going to 0, and we have seen that the limit of sin x by x, that is equal to 1, but this limit is not equal to 1, because here what we have to do is that we need to use the same thing. So, we write limit x going to 0 sin 3x divided by, if I write 3x, then here I have whatever is inside sin, I am dividing by that. This limit is equal to 1, and but then I have to multiply this by 3 to get this same function. So, this limit is equal to this limit, and now because I am dividing by the same 3x which is inside sin 3x, then I can simply write, or if you want you can write one more step, this is equal to limit of y going to 0 sin of y by y times 3, and where y is equal to 3x, and then this is equal to 3. So it is a good idea to like change it into another variable y and then use the formula for sin y by y, right. So at least in the beginning you should do like this to avoid the mistake that this is not equal to limit sin 3x by x, x going to 0, this is equal to 1, this is wrong. Right. So, the next thing that we will talk about is what we call infinite limits. So, I will just explain by an example. So, suppose you look at, consider f x equal to 1 by x for x not equal to 0. So, this function if you see, as we approach 0, as x becomes a small positive number, 1 by x becomes larger and larger. So, the graph of this function is this rectangular hyperbola, and for negative x we have this, as x is negative. So, what happens is that as x tends to 0 plus, this means from the right 1 by x becomes larger and larger. And as x tends to 0 minus, that means that from the left if you approach 0, then 1 by x becomes large negative number. So, we will explain this more rigorously, but what we say, so in such cases we say limit of 1 by x as x approaches to 0 from the right, this is equal to positive infinity, and limit of x going to 0 minus of 1 by x, this is equal to negative infinity. So, this simply means that if x is a small positive number, then 1 by x becomes a large positive number, and if x is a small negative number, then 1 by x becomes a large negative number. So, we use these symbols positive infinity and negative infinity to just say that. In the next class, I will make it more rigorous and define when we say that the limit at a point is positive infinity or negative infinity, and then we will see some more examples. So, in the next class, we will make it more rigorous about this limit being positive infinity and negative infinity, and then we will see some more examples on this. Thank you.